Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on image denoising using deep image prior. I already have a tutorial on this topic on my channel, but in this video I'm going to use a different model. Let's get started. As I said in this video, I'm going to talk about image denoising using deep image prior. A deep image prior based neural network is a deep learning architecture that is designed to perform image restoration tasks such as denoising, inpainting, or super resolution, and so on. And it does that without requiring any prior training data. The idea behind DIP or deep image prior is to use a randomly initialized neural network to model the structure of the image during the restoration process, as opposed to relying on a large dataset for training. Unlike traditional neural networks which learn from large amounts of labeled data, a DIP network learns directly from the image itself during the optimization process. The main principle is that deep networks are powerful enough to capture the inherent structure of natural images, which allows them to restore corrupted images through optimization. So as I said, a key feature of DIP is that it doesn't rely on any external training set or pre-learned features. The only input it requires is the noisy or degraded image, and the network parameters or weights are randomly initialized. The network is then trained to optimize the image's structures through a loss function that measures the difference between the output of the network and the target image, for example, original image or a clean version. DIP or deep image prior networks optimize the input of the neural network, for example, a noisy image, using a gradient-based optimization process. This process involves minimizing the loss function that measures the quality of the restored image. During this process, the network parameters do not get updated, as it is in the standard training. Instead, the input image or some part of it, like noise, is updated, gradually refining the image to resemble the clean version. The neural network is initialized with random weights and does not require pre-training. This random initialization is crucial because the network essentially serves as a prior for the image restoration task. Deep image prior based networks are primarily used for image restoration tasks, which include image denoising, image inpainting, super resolution, deblurring, and colorization. Denoising is one of the most common applications of the DIP networks. The goal is to remove noise from an image and restore it to a clean version. DIP networks learn the natural image priors that allow them to fill in missing information and reduce noise. In the case of the image inpainting, DIP can be used to fill in missing or occluded regions of an image. The network learns to reconstruct missing pixels based on the available context, which is useful in applications like object removal, painting restoration, and photo editing. In the case of the super resolution, the goal is to increase the resolution of an image. DIP networks can be trained to enhance the resolution of a low-quality image by learning the underlying high-frequency details and structure. In the case of the deblurring, DIP networks can be used to remove blur from an image, which can occur due to camera shake, out-of-focus shots, or motion blur. The network learns to reconstruct the sharp details of the image. In the case of the colorization, DIP can be used for colorizing grayscale images. The network learns to fill in the color information based on the image's natural structure and prior knowledge. There are different types of DIP-based networks. While the core idea behind DIP networks remains the same, different variations have been proposed to address specific types of image restoration tasks, like basic DIP or DIP with residual blocks, DIP with learnable noise inputs, or DIP with regularization, and finally DIP with generative models. Let's talk about the basic DIP. The original deep image prior approach is simple and works by optimizing the image's input through a neural network trained from scratch. It typically uses a UNet or a similar architecture where the network architecture is designed to preserve spatial information. DIP with residual blocks. This variant of DIP includes residual blocks in the architecture. A residual block allows the network to learn residual functions which are easier to optimize and can help with better feature learning, especially for deeper networks. The residual connections add skip connections to the network layers to allow information to flow more efficiently, improving performance. DIP with learnable noise inputs. Some variations of DIP networks allow for learnable noise inputs rather than a fixed noisy image. The noise input is treated as a trainable parameter. During optimization, the network adjusts this noise to gradually produce a clean image, effectively learning the image through noise manipulation. DIP with regularization. Many DIP-based networks incorporate a regularization term such as total variation loss to encourage smoothness and prevent the network from producing noisy or jagged images. This type of DIP is helpful for tasks where preserving image structure is critical, such as in-painting and deblurring. DIP with generative models. Some DIP variations combine generative models with the deep image prior approach to refine the generated image further. These models typically involve a discriminator that helps guide the optimization of the image input by providing feedback on its quality, ensuring that the restored image appears more realistic. The deep image prior based network that I'm going to be using in this work is with residual blocks. And as you can see, this is the architecture of my network. First, I have a learnable noise input. So the learnable noise serves as the input to the deep image prior network and is gradually adjusted by the network to restore the image. So the encoder here captures the high-level features, and the decoder reconstructs the image. The residual blocks in both the encoding and the decoding paths help refine the feature extraction and image reconstruction process. As you can see here, these are the residual blocks. And then we have bottleneck, and then upsampling, and then decoder. So with the encoding, we always have downsampling, and then with decoding, we have upsampling. And then the final output, which is here. Let's go to Google Colab and show you the code. But before we go to Google Colab, let's talk about bottleneck a little bit. After encoding, the feature maps are passed through a bottleneck layer, which further processes and compresses the feature maps. This bottleneck layer is followed by another residual block to refine the learned features. And then we have upsampling, and then decoding, and then output layer. Okay, let's go to the Google Colab. So we first mount our Google Drive to the Colab environment, as you can see here. And then we import the libraries that we need. Then we're going to be loading and pre-processing the image. I'm going to be adding some Gaussian noise to the image. And this is the original image. This is the noisy image, as you can see. And we're going to be denoising this image. And then here we're going to be importing the necessary libraries such as PyTorch modules for neural network operation, image processing tools like PIL for image handling, and utilities for displaying the outputs, as you can see here. And then here we're going to be checking if CUDA or GPU is available and assigns the appropriate device. If the CUDA is not available, we just use CPU. And then here we're going to be computing the total variation loss, which penalizes the total variation in the image. It encourages spatial smoothness by minimizing differences between neighboring pixels. And then here is the residual block definition. This defines the residual block using two convolution layers with ReLU activation, as you can see here. This block helps in learning residual functions, which can facilitate better training and feature learning in deeper networks. And then here is the DIP network with residuals. So this defines a deep image prior network with residual connections. It includes encoding ENC1 and ENC2 and decoding DEC1 and DEC2 layers with pooling pool1, pool2, and upsampling up1 and up2 operations. The network reconstructs an image from a noisy input using residual learning principles. And then here we are setting up the training environment with parameters like learning rate, loss function, optimizer, and training iterations. As you can see here, these are the optimizers. And then the training loop here executes a training loop where the model is optimized to reduce the mean squared error, or MSE, between the output and the target image, the noisy image here. And then here we have early stopping. Early stopping is a technique used to prevent overfitting during training. Here it is used to halt the training process if there is no improvement in the peak signal to noise ratio, or PSNR, over a set of number of training iterations, which is also referred to as patience. This helps avoid unnecessary computation and prevents the model from overfitting noise in the data. So the best PSNR tracks the best PSNR achieved so far during training and is initially set to 0, as you can see here. And the best output stores the output image corresponding to the best PSNR. And patience defines the number of iterations to wait for PSNR improvement before stopping training. In this case, it's set to 20. This means if the PSNR does not improve for 20 consecutive iterations, training will stop. And the no improve count tracks how many iterations have passed without improvement in PSNR. If it reaches the patience threshold, the training will stop early. So as you can see, this is the training loop, and we have 5,000 iterations here. This optimizer 0 grad clears the gradients from the previous iteration to avoid accumulation. And then here we pass the current noise tensor through the model to get the output. And then here we're going to be computing the loss by adding the mean squared error loss between the output and the target image, as well as a total variation loss to promote smoothness. And then here we're going to be computing the gradient of the loss with respect to the model parameters. And then here we're going to be computing the model parameters using the computed gradients. And then here we're going to be storing the current loss value for plotting and analysis. And this part of the code is used to smooth the output image by applying an exponential moving average. This helps reduce noise or fluctuations in the output during training. And alpha here is a smoothing factor. Running output here stores the smooth version of the output. This condition checks if it's time to log the current PSNR value. So here is where we're going to be computing the PSNR and check if we need to stop early. Overall, in this piece of code, we're going to be computing the peak signal to noise ratio PSNR between the target image and the current output image. PSNR is a common metric used to evaluate the image quality, where higher values indicate better quality. But then we're going to check it here. If the current PSNR value is higher than the best PSNR seen so far, we're going to be updating the best PSNR to the current value. And then we're going to be storing the corresponding output image, and then we're going to be resetting the no improvement counter. But if the PSNR did not improve, we're going to increment the no improvement counter. If there's no improvement for the patient's number of iteration, it triggers early stopping, which happens through the break here. And then here we're going to be showing the noisy image input and the output. And I've already run the network, and you can see this is the output and this is the input. And you can see that the output has become denoised much better than the noisy image input. And this is the loss value per each iteration. You could see that the loss value goes down as the iteration increases. You could see that the denoised output is not bad as opposed to the noisy input. And that's about it. Thank you so much for watching this video. I hope you liked it and also found it helpful. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.